Why does a curve in two-dimensional space have zero area? You might say it's infinitely thin. You might say it's one-dimensional. Or you might say that zero area is nonsense. But how do you rigorously decide with integrals and the Jordan measure? We want to focus on how to visualize this mathematical theory. In this video, you will explore why this curve has zero Jordan measure using three different methods: integrability of indicator functions, the rectangular covering theorem, and Sard's theorem. There are many definitions of zero Jordan measure. Let's start with one of them. A set S in n-dimensional space has zero Jordan measure, or zero volume, if and only if, for some rectangle R containing S, the indicator function chi S is integrable on R. In other words, S is Jordan measurable. Also, the integral of chi S over the rectangle R must be equal to 0. If so, write that the volume of S is equal to 0. In two-dimensional space, zero area is the same as zero Jordan measure. Remember, the indicator function evaluated at x is 1 if x is in S, and it's equal to 0 if x is not in S. Also, recall that the indicator function is integrable on a rectangle R if and only if the supremum of the lower sums of chi S on R is equal to the infimum of the upper sums of chi S on R. In other words, the lower integral on R must equal the upper integral on R. If any of these definitions on integration or the Jordan measure are new or unfamiliar, then now is a good time to pause and learn about them. The rest of the video relies on a basic introduction of these definitions. So let's apply this definition to our curve in R2. This curve lies in two-dimensional space. We place our curve inside a rectangle R with a partition P. Since it is a partition, notice the subrectangle interiors do not overlap. Let's compute the lower sum and upper sum of the indicator chi S with this partition, P. For the P lower sums, notice each subrectangle has a point X which does not belong to S. This means chi S of X is 0. The infimum of chi S on each subrectangle is therefore equal to 0. Since every subrectangle contributes 0, the P lower sum is itself 0. For the P upper sum, let's look at this subrectangle first. Notice this subrectangle has a point X which does belong to S. This means the indicator function at that point is equal to 1. Since the indicator function is either 0 or 1, the supremum on that entire subrectangle is therefore 1. Let me put this subrectangle here to indicate that it is equal to 1. These other subrectangles also have supremum equal to 1 for the same reason. So let me add a rectangle on each of them. The other subrectangles do not have any points of the curve in them, so the indicator function is always 0 on the entire subrectangle. The supremum of the indicator function is therefore also equal to 0 on each of these. So that means by totaling the area of the subrectangles which are equal to 1, we get the P upper sum, and this is calculated to be equal to some non-zero value, equal to this total area. For the sake of concreteness, let's say it equals 3.4. This estimates the area of S, if it exists, and tells us it's either at most 3.4 and at least 0. How can we improve this estimate? By refining our partition P to a new partition Q. In other words, let's cut up the rectangle a little bit more. Repeating the same process, every single subrectangle has a point which does not belong to S. Thus, the Q lower sum is equal to 0. Similarly, these subrectangles have a point which do belong to S. These other subrectangles do not. Thus, the Q upper sum is equal to the total area of these subrectangles. Since the partition has been refined, the Q upper sum is smaller than before. Let's say it equals 0.9. Again, if the area of S exists, then this shows that it must be between 0 and 0.9. By refining our partition more and more, we can keep reducing the size of the upper sum. This idea can be captured with a nice diagram. For every partition, the lower sums will always be equal to 0. Thus, the lower integral is also equal to 0. On the other hand, the upper sums will be positive, and as we refine our partitions, the upper sums will get smaller and smaller. We should be able to make the upper sums arbitrarily small, so the infimum of upper sums will equal 0. Thus, the upper integral itself is also equal to 0. This proves that the indicator function is integrable on R, and also that its integral is equal to 0. That's exactly the definition we started with. This definition is useful for proving general properties of zero-volume sets, but it is very rigid and complicated to verify for specific examples. Since we have illustrated our first method for showing a set has zero Jordan measure, let's move on to the second method, the rectangular covering theorem. A set S in n-dimensional space has zero Jordan measure if and only if, for every epsilon bigger than 0, there exists finitely many rectangles such that 1, the set S is contained in the union of the rectangles, and 2, the total volume of these rectangles is at most epsilon. At first glance, this might seem almost identical to what we just discussed with partitions and upper sums. But there is a subtle yet crucial difference. The rectangular covering theorem allows rectangles to have overlapping interiors. Partitions of a rectangle do not permit this property. It might seem like a minor convenience, but it's surprisingly useful to have this extra flexibility. Let's see how to visualize this theorem with our curve. Start by fixing an epsilon. Say epsilon is 7. Remember, we need to choose finitely many rectangles satisfying two properties. First, they cover S, and second, their total area is less than epsilon. Let's try a first attempt. This covers S with one big rectangle, but it seems like the total area is way too big. Let's pick a better covering. This also covers S, and the total area is smaller than epsilon. Notice the total area counts the overlapping areas multiple times. Now, does this prove that S has zero Jordan measure? Not quite. We need to consider smaller values of epsilon. Fix a smaller value of epsilon. Let's say epsilon is 0.8. Since epsilon is smaller, this choice of rectangles won't work anymore. We will need to use even smaller rectangles to cover it. Once again, this covers S, and the total area is less than epsilon. We can repeat this process for arbitrarily small values of epsilon, and this will prove that S has zero Jordan measure by the rectangular covering theorem. This theorem gives incredible flexibility with your choice of rectangles, but it can be technically complicated to actually define a good choice. Each rectangle needs to be chosen very carefully in terms of S and epsilon. There's a lot of messy details that you would need to write out. This conundrum leads to Sard's theorem, our third and favorite method for showing a set has zero Jordan measure. Fix positive integers k and n with k less than n. Let R be a rectangle in k-dimensional space. If f is a function with n-dimensional outputs that is continuously differentiable on an open set containing R, then its image has zero Jordan measure in n-dimensional space. Informally speaking, Sard's theorem says that a set has zero Jordan measure if you can smoothly parametrize it with fewer variables than the dimension of your space. It's a really lovely theorem because it is super easy to check in many specific examples. However, many sets cannot be parametrized easily or at all, so Sard's theorem cannot necessarily be used in every situation. In the case of our curve, we are lucky enough to be able to apply Sard's theorem, so let's visualize it. Assume our curve in two-dimensional space can be parametrized by a C1 map F from a closed interval AB in one-dimensional space. For example, imagine an ant walking along this curve. It starts here at time t is A and ends here at time t is B. The interval AB is a rectangle R in the one-dimensional domain. The image f of R is equal to our curve S in the two-dimensional codomain. Assuming our map F is C1 on an open set containing our interval, Sard's theorem automatically proves the curve S has zero Jordan measure. That is slick and smooth. No need to break a sweat. This outcome is actually so magical it's kind of hard to believe. How does the proof of Sard's theorem actually make this magic happen? The basic principle is that the parametrizing map F gives a systematic procedure for using the rectangular covering theorem. We can illustrate the proof with our curve. The proof begins by fixing epsilon. Say epsilon is 1.4. Next, partition the rectangle in our domain space. Let's chop it into 3 parts. Each of these pieces in the domain correspond to segments on the curve in the codomain. For each segment, we will place one rectangle to cover it. The size of the rectangle will be chosen to be as small as possible. The width goes from the minimum x value to the maximum x value, and the height goes from the minimum y value to the maximum y value. We repeat this for each segment. Assuming we've chopped our domain into small enough pieces, the total area of these rectangles is smaller than epsilon. But for a smaller value of epsilon, all we need to do is repeat this process. So we partition the domain into smaller pieces. Then we place the rectangles on each mapped segment. The total area is now even smaller. We can repeat this argument for arbitrarily small values of epsilon. So S has zero Jordan measure by the rectangular covering theorem. And that's the main idea behind the proof of Sard's theorem. There's one tricky caveat. Why did we need the parametrizing map F to be C1? This assumption means that the ant travels smoothly. In other words, the ant cannot travel too far over a fixed unit of time. This allows us to control the size of the rectangles covering each segment. If the rectangles got too big, we could not guarantee that the total area is small. In technical jargon, this allows us to apply the mean value theorem. However, the true explanation is way more shocking. The statement of Sard's theorem is actually false for continuous maps. Indeed, there actually exists continuous bijective maps from a one-dimensional interval to two-dimensional square. These mathematical demons are called space-filling curves. But that dark tale shall not be uttered here. Instead, we will end by honoring the three methods for proving a set has zero Jordan measure: the definition with integrability, the rectangular covering theorem, and Sard's theorem. Each of them illustrated why our curve has zero area, but none of them can take away its spirit.